In this lecture, we look at heat and work. Heat and work can both change the internal energy of a system. If we apply heat to a system, so Q flows in, the internal energy increases. If we use a refrigerator, it extracts the heat from the system, and the internal decreases. Similarly, if work is done by the system, so that the piston moves up, the internal energy of the system decreases because that energy has gone into the work. Or if work is done on the system, something pushes the piston down, then the internal energy increases in the system. Well, what if we put heat in and work is done? What happens to the system? Well, the change in the internal energy is equal to the difference between the heat input and the work done by the system. This is the first law of thermodynamics. What is work? Well, work is the integral of the pressure times the change in volume, the differential change in volume dV. If we were to look at what this integral looks like and graphically, we look at the plot of the pressure versus the volume. If our system starts out with an initial pressure and initial volume indicated by the black dot, and we want to travel over to a final pressure and a final volume by some path. Here we're taking one that goes straight across and then straight down. Then the work done in going from the initial to the final state of the system is given by the area under the curve. This is the integral of P dV, so it's the area of that rectangle. And it is positive because the change in volume is positive and the pressure is positive. There's no such thing as negative pressure. So the work is greater than 0. If we take a different path, the work is still greater than 0, but now the work is reduced. Or we can even take another path where the work is even smaller. So there are many different ways to get from the initial to the final state, so the work can be many different things. Let's look at an example of a heat engine where we convert heat to work. How much work occurs as the system follows its closed path? So again, we're looking at a pressure versus volume plot, and we start at the left at the initial volume and initial pressure and go to a final volume and a final pressure. And as we go across this, the first leg, the horizontal line, we're expanding at constant pressure. So the pressure always stays at P sub I. So the work on this leg of this first leg is equal to the pressure P sub I times the difference in the volume, Vf minus Vi. So it's just the area of the rectangle below that curve. Then if we decrease the pressure at constant volume, the second segment, well, W2 is equal to 0 because there's no area underneath that segment. The last leg, as we go back from the final value to the initial value, we increase the pressure linearly as the volume decreases. So we have that W3 is equal to this value, the area of this trapezoid. So it's 1/2 times the average value of the pressure times Vi minus Vf. Notice that it's Vi minus Vf. And this is negative because we're going from a larger volume to a smaller volume. We're going from Vf and decreasing the volume to Vi. So this is negative. So the work is going to be negative. So the net work that has been done in going around this cycle is equal to W1 plus W3, which is, if you do this addition, you get 1/2 Pi minus Pf times Vf minus Vi, or just turns out to be the area of the triangle enclosed by the path. On returning to the starting point, the change in internal energy has to be zero because we're now back at our original starting point. So W net has to be equal to the heat that has been added. So in other words, the heat added becomes the net work done by the system.